In this lesson, I am going to discuss properties of determinants. Suppose that we have two n by n matrices, A and B. We want to find the possible relationships among determinant of A, determinant of B, and the determinant of the transpose, the determinant of a scalar multiple, the determinant of the sum, and the determinant of a product of two matrices. Here is our first result. The determinant of the transpose of a matrix is equal to the determinant of the original matrix. Let us verify this for a 2 by 2 matrix. Here, the determinant of A is equal to AD minus BC, and the determinant of A transpose, it's still equal to AD minus BC. Let us verify this result in this 3 by 3 matrix. So first, I will compute the determinant of this matrix by using the cofactor expansion along the second row because it has exactly one non-zero entry there. The determinant of A is equal to plus minus, and then copy that entry and remove the row and column containing 2. Multiply that with the determinant of the matrix that will result. Therefore, this is negative 2 times 5 minus 2, that is 3. So this determinant is equal to negative 6. Let us compute for its A transpose. We will compute the determinant of A transpose by computing the cofactor expansion along the second column. In this case, we have plus, minus, and then 2. Delete the column and the row containing that. We get 1, negative 1, negative 2, 5. And this is negative 2 times 5 minus 2 again. So it's equal to negative 6. Take note also that the matrix that resulted here is the transpose of this matrix over here. Next, we want to investigate the determinant if we multiply a matrix by a scalar k. Previously, we've learned that we can pull out the common factor here for each row. So we can pull out k here, and k here. So therefore, we will end up with 3k's being pulled out and then the determinant of the original matrix. We can generalize this result for a matrix of size n by n. So similarly, just what we did in the previous slide, we can simply pull out the k's in each row. So if that is the case, we will pull out n k's. Hence, the determinant of k times A is equal to k raised to n times the determinant of A. Let us evaluate the determinant of this matrix, A. Take note that A is equal to 10 times this matrix over here. So therefore, the determinant of A is equal to 10 raised to 3 times the determinant of this matrix. And how do we get the determinant of this matrix? I will get the cofactor expansion along the second row because this row has exactly 1, 0. I will have a negative 1 there, times the determinant that will result when we remove the row containing 3. Therefore, this is equal to negative 100 times negative 2 plus 12. So that's 10. We get negative 3,000. Next, let us investigate the determinant of a sum. Let us compute the determinant of each matrix here. The determinant of A here is 5 minus 4, that's 1. The determinant of B is 9 minus 1, that's 8. And the determinant of A plus B is equal to 32 minus 9, that is 23. So therefore, from this example, we now know that the determinant of a sum is not equal to the sum of the determinants. We cannot sort of distribute the determinant if the operation inside is plus. However, for the case of products, it turns out that the determinant can be sort of distributed, as we will see in the next slide. Here is our next big result. The determinant of a product is equal to the product of the determinants. Let us recall that when we studied 2 by 2 matrices, we've learned that A is invertible if and only if the determinant of A is not equal to 0. Now, it turns out that this result is true for any n by n matrix. We have this theorem: if A is any square matrix, A is non-singular or invertible if and only if the determinant of A is not equal to 0. Moreover, if A is invertible, the determinant of its inverse is simply equal to the reciprocal of the determinant of the original matrix. For example, which of the following matrices has an inverse? We've just learned that we just have to compute for its determinant. Let us observe that B here is an upper triangular matrix, so therefore its determinant is simply the product of its main diagonal entry. So we have 4 times 4 times negative 2. This is equal to negative 32. However, for the determinant of A, notice that the third row is simply a multiple of the second row. And if that is the case, what happens to the determinant? The determinant will be equal to 0 if you have a row which is a scalar multiple of another row. So therefore, since the determinant of A is equal to 0, A has no inverse, whereas B has an inverse. Let us recall the following equivalent statements that we have for a matrix to be invertible. Now we can add to this list the last theorem that we had, that is the determinant of A is not equal to 0. Now take note here that we can use this for systems of linear equations. Why is that? If we look at statement 3, AX equals B has exactly one solution if and only if A is invertible, and we know also that A is invertible if and only if the determinant is not equal to 0. Let us go back to systems of linear equations and apply what we've just learned. Which of these systems has a unique solution? Recall that a system will have a unique solution if the coefficient matrix is invertible. And the coefficient matrix is invertible if and only if its determinant is not equal to 0. So that is exactly what we are going to do with these two systems of linear equations. Let us first consider this one and let us form the coefficient matrix. We have 0, 2, negative 1, 3, negative 2, 1, 3, 2, negative 1. And take note that this is exactly the same matrix that we had earlier, wherein the third row is a scalar multiple of the second row. So therefore, the determinant of this matrix is equal to 0. Therefore, the answer here is no. It does not have exactly one solution because the matrix A is singular. For our next item, take note that the only difference of this one with the previous item is the sign over here. So therefore, I will now turn this into A plus. Let us find the determinant of this matrix. Take note that I already have a 0 here. So I want to have a 0 here so that we will have a column containing exactly one non-zero entry. I can do that by subtracting row 2 from row 3. We will have 0, 4, 0. And take note that it was just a replacement row operation, so the determinant of these two matrices will not get changed. We now get the cofactor expansion along the first column. This determinant is equal to plus minus, we have negative of 3, and then multiply with the determinant that will result when we remove this row and this column. We get negative 3 times 0 minus negative 4. That's positive 4. We get negative 12. Hence, since the determinant is not equal to 0, this one has exactly one solution.